But good afternoon, and thank you very much for the opportunity to speak to all of you here. And thanks for the effort being put by all of the leadership here to make this work. Uh, Basically, I actually my topics cover. There are three different topics here that I do cover in the talks that I have listed, and the first one of them is retitled Rebooting Computing, the Search for Post-Moore's Law Breakthroughs. And I just would like to get cues always that you guys can hear me. So you can hear that, right?
Yep.
Okay, great.
Yes.
And the idea basically is that we are very much witnessing to approaching the end of a couple of very important, observations that were made. One of them with the Moore's law, which by virtue of which we always have been taking it for granted that chips will be faster every year, basically actually doubling up the speed every 2 years, and also that the transistors can be made smaller. They will continue to be functioning, and the power, basically consumption will be proportional to the size of those, so it will be, kept in, under bounds. And these two now are unfortunately a problem. The first one of them was a source of performance and speed because we can run things faster. The second one was allowing us to add massive parallelism on the chip, and now we are also hitting that limit as well. So as a result, if we would like really to continue to harness the speed of the computing to move the society forward, we're going to have to start thinking all over again about computing and how we're going to be actually providing such actually high performing machines in the future. And our eyes then will start to go and look at perhaps new material or new architectural ideas that are not necessarily digital, even could be very much transformative and revolutionary things. And along those lines, there has been a number of things that have been proposed and a lot of ideas that have been at least partially implemented or somehow implemented, even including quantum computing, including coming up with a new device, which is a memristor, and showing that, for instance, a set of these can be used to solve things such as linear algebra type of problems, as well as machine learning types of applications very efficiently. In addition, of course, to brain-inspired computing, things like neuromorphic. And brain-inspired is very important as we look today and we see, for example, that the top machine in the world, actually, I would say the third top, for example, is taken actually consuming 15 megawatts, while the brain, in doing what it's doing perfectly, only consumes about 20 watts. So we're going to be trying to look at some of these new architectures and new ideas for how to engender computers that are dramatically different from what we have for the future. So that's what this talk is about. Shall I go to the next, or entertain any questions here?
I would say go on and just tell us about the rest of your talk.
Okay. The second one basically here talks about what's happening in terms of very high speed computing and high performance computing. We're looking to go to the next level, which is the exascale type of computing that will be like a million trillion calculation per second, if you will. And we looking at achieving this in the next actually couple of years. But then while we're really actually moving to that type of great milestone, we are seeing a lot of demands by applications, particularly the explosion of data. We're looking into like seeing by next year, something like 50 billion connected device in terms of IoTs and the like to the internet. So there is actually this kind of really many different developments that are happening in the same time and creating an ecosystem between high-speed computing, big data, AI, and IoT and the like, that more or less will be able to support smart life and very smart kind of world again around us, if they are put together and if they are already converging actually in a natural way, but actually this needs a little bit more guidance from the community. So essentially this here looks at what we are calling the digital continuum, from on the top, actually all the little instruments at the devices, smart sensors, and the like, and going in that pyramid here all the way until the bottom where you see the big data centers and the HPC, and trying to look for ideas into how to make this work harmoniously. So, for example, you could be making decisions at the top, at the edge, while you could probably actually getting some help from a model-based kind of an application where the models are run in the bottom at the data center, and then maybe there are other things happening in between as well. You could be doing inference at the edge while you are actually calculating weight somewhere else in the whole continuum, depending upon what is happening at any given point of time. So we look at this, the progress in each one of those areas with emphasis on HPC and exascale, and then we show also the types of challenges and opportunities coming up from the explosion of data and the reintroduction of AI and again the growth in IoT, and try to really think of what's there to be complementing all of these and how they deal with this entire big pyramid of capabilities in a harmonious and seamless way. The last talk out of this here group is more actually oriented towards, I would say, more specialized high performance computing type of audience, where essentially it looks at the new additions of supercomputers and the fact that it's becoming extremely hierarchical, and extremely also massively parallel. And while one of the very important and very actually of challenges here would be data movement. So data movement in such kind of huge hierarchy could in fact be extremely costly in terms of energy and in terms of latency. So we're looking at how can we create such kind of architectures, such kind of massive systems, while basically we can exploit locality, both from the system level, from the hardware level, and from the application perspective in a coordinated way. Productive is a key term there because we'd like to do that in such a way that the programmer does not shoulder the big burden of doing all of this here by hand, but rather a lot of it will be taken care of by the system. So there's an attempt in there to see what would be the minimum amount of information that need to be conveyed by the programmer, and how the system can intervene really when we need it to intervene to help without really burdening the programmers further. So that will be actually my third talk in this group here.